So this is a demonstration or a video, I guess a screenshot, of what we did today in class, and that's November 28th. We had two force plates, which are basically scales. They were calibrated to read in one being the positive direction, one being the negative direction. So I believe this was, let's see, mod 11 on 14. I forget who did these. But anyhow, might be Sam on Catherine, something like that, I don't know. But they had these things, they pushed them at each other, and we tried a number of different circumstances. If you look at the patterns, within the realm of uncertainty, we have the exact same pattern above as we do below. No matter what the situation, whether they were just pushing against each other, or they were pushing vertically instead of horizontally, whether someone was pushing someone back, whether they were sitting in chairs pushing off of each other, we always saw that the two forces were the same magnitude. In other words, if this one was at plus 100 newtons, that one was at negative 100 newtons. The key thing about this is it allows us to develop a rule of interactive forces, which relates to Newton's third law. Newton's third law is not for every action there's an equal and opposite reaction. If you doubt me, go run into a concrete wall. I guarantee you the wall won't care. But on a more serious note, you want to make sure that you understand what an interactive force pair is. So interactive forces are a pair that has two forces. They act in opposite directions, they have the same magnitude of force, and they act on different objects. So again, in this case, if we note, I've got person 1 on person 2 on person 1. You cannot have interactive forces acting on the same object. The other thing we noticed was that although these forces were the same, in the case where they were pushing on each other on rolling chairs, the student who was in the rolling chair and who was the more massive student ended to roll back less. So that goes back to Newton's second law. Acceleration is equal to net force divided by mass. If you end up having two equal forces but less mass, you'll have a bigger change in motion. That's really hard for a lot of people to understand. So the example that we did in class was we jumped up and down. We jumped up, the earth pulled on us, but we also pulled up on the earth. So why didn't we notice the earth jump up at us the same way that we fell back down? The simple answer is the earth has a lot more mass, like quadrillions, squabillions more times more mass. In fact, its mass is about 6 times 10 to the 24th kilograms, whereas your mass is probably less than 100 kilograms. So you can see that a tiny force acting on the earth, by comparison, seems like a pretty good one-size force acting on us. Anyhow, hopefully that's a recap for people who were not here today.